So you're going to look at the set of polynomials with real coefficients. Okay, polynomials with real coefficients such that they take positive values whenever the real number that you're plugging in lies in the open interval from 0 to 1, let's just say. So you should check that any convex combination of these things is still positive on the open interval from 0 to 1, because the value is just going to be convex combinations of positive things. Right. So this is a sort of a, an more abstract example of some convex set. And here's convex sets. Here's another one, which I'm not sure you can do at the moment, but you will at some point be able to do. There may even be a homework problem about it eventually. Let's look at all n by n matrices that are, well, in this case, symmetric, and all of the eigenvalues are positive. Okay, so these are called positive definite matrices, and one can prove, and probably not yet because we haven't done enough, but one can prove that this set of matrices is convex. That convex set is very important because people often want to optimize over that set, and optimizing over a convex set is easier than optimizing over an arbitrary set. Okay, so that's just some more examples, just to show you that not all convex sets are polytopes or something like that. They come up naturally in various parts of math. So, so then now some definitions that are going to be sort of reviewed. So I want to call a point in X. So X is just some subset of Rn. I'm not necessarily assuming that it's convex for this, but if you want to assume that it's convex, that's fine for this purpose. This is an interior point. An interior point if whenever you have, if V lies inside of an open set U that's contained in X, and that's going to be where for some open set U. Okay, so it says that X. So the picture is that you have some whatever, some space here, and maybe it contains part of its boundary, and maybe it doesn't contain other parts of its boundary. Right, it contains that part, maybe it kind of contains that part and not that part, like this, and that would be our set X, which might be, might look like this. It could also, I guess, have something that sticks out like that, right? This is just going to be some arbitrary set, and I want to call my point an interior point. So for instance, this over here, that would be an interior point. Okay. Just says that it has a neighborhood inside of X. And I want to call I want to say that B lies in the boundary of X. So this is a boundary point. And it's what you think. That's if you intersect X and you intersect the complement of X, both non-empty, and that's going to be for all open U containing V. So what's written in the notes is slightly incorrect. There's no if. Just failed to write the word if. And it's supposed to be U containing V. It's important that U contains V. The notes it just says for all open U, which is of course ridiculous. So the point here is that I'm looking at some point on the boundary. Let's say like, for instance, up here, right? And if I take any open set, then it intersects both X and not X. Right? Now, it's not important that this point be in X, right? I just said that this is a boundary point. So this is the boundary of X. And it's not important that this point be in X or not in X, right? It could be that point. It could be, let me circle this around. Right? It could be even say this point. Right? Those are both boundary points. One of them lies in X, one of them doesn't lie in X, but that's not relevant. And I'm going to say that X bar is going to be X union the boundary of X, and that is called the closure. Closure of X. That's probably hard to read. Yeah. There's a line going through it. Okay, so what's the closure of this set? What does it look like? Fill in the dotted line. Yeah, just fill in the dotted lines, right? So this stuff. Closure. And what you do is you fill in the dotted lines. You have to add in this stuff. There you go. So that gives you the closure. Okay, that should be basically familiar from Math 222 for multivariable calculus. This picture should be familiar. So, proposition, and this is more or less what we proved a couple lectures ago, says that the closure of X is the set of limits of sequences of points in X. It's the limit of xk such that the sequence xk contained in X converges. This is not saying that the sequence converges in X. It's saying it converges in Rn. Right? So, suppose I could have just said actual, I could have said V here instead of Rn. This actually doesn't depend on it being Rn, it just depends on it being a real vector space. So maybe take it in that generality. But the point is that this sequence needn't converge in X, right? So this red point, remember, wasn't in X. But if I take a sequence of points converging to it, I can take a sequence of points converging to it where all the points that are converging to it lie in X, even though the point itself doesn't lie in X. That's why I want to throw it in. So it's X union the set of all of its limits of sequences contained in X. And the proof is just it's some proposition from before. We showed that a set is closed if and only if it contains all of its limit points. And so what we're doing is we're just saying, all right, well, if it didn't contain all its limit points, then just throw them in. And the point is that you don't have to iterate that procedure. You could imagine that maybe you threw them in, and now you have to take limits of points, the stuff that you just threw in, and you have to keep doing that ad infinitum. But in fact, just doing it once is enough. And it's not hard to show that. Okay, so for example, is the following set open? So what that is, that's a straight line segment that's missing its endpoints. Is it open? I see one yes and one and. Online, I'm not getting anything. Aha, and we have one depends on which space. So how does it depend?
In R2, it's.
No, it's
no,
not.
sorry, it's gonna be,
Give me the one with the easy answer.
the R1 is,
Yes. Inside the line, this is open. This is just an open interval. Okay, how about in R greater than or equal to 2?
oh, it's no.
It's just no. The answer is no. It's not open or closed, but it's definitely not open. Right, because this thing has no interior, because if I take a point in here, then, you know, there's a neighborhood. So it's sort of all boundary. Yeah. We could fix this by defining a notion of relative interior, but I'm not going to do that. There is a way to make it so that you can tell that this thing feels like, you know, from inside the set, it feels like it's open. But externally, where it's embedded, it does not feel like it's open. And as I said, there's a way to fix that by defining a notion of relative interior, by not paying attention to what sort of set you're in, sort of, but only sort of, because you have to know that there are boundary points and that those boundary points exist outside the set. But anyway, one can define these things away, but we're not going to do that here. That's maybe for a topology course or analysis course of some sort. Here's what we need, and that is that if X is convex, then the closure of X is convex. So taking closures doesn't ruin convexity. And the proof is, I mean, I have to follow your nose here. We know that the closure is consisting of limits of sequences. So let's just take a limit of sequences and show that it's still inside the closure. So, well, you'll see. Saying it's going to be longer than just writing it here. So if we take a sequence Vk converging to V and Wk converging to W, regardless of you know, whether these points are in X or out of X or whatever, then if we take these two sequences, then if I take alpha times the first one plus beta times the second one, then this converges to alpha times V plus beta times W. That's just a true statement. It has nothing to do with convexity. It has to do with, you know, limits of sequences and the fact that you know, that addition is linear, limits commute with addition and this kind of stuff. Okay, so now if you have Vk is in X and Wk is in X for all k, and if you assume that alpha plus beta equals 1, then what you get is that alpha Vk plus beta Wk, what do you know about this point? This is now a convex combination of Vk and Wk. So if we assumed that these are both in X, then this convex combination also lies in X, right? So that's in X for all k by convexity. What letter does the picture cut off here? It's good the whole way? Oh, okay, that's nice. And that implies, right, so remember, think of alpha and beta as being fixed. Don't think of them as varying. Just think of them as fixed. They're just some fixed scalars that happen to add up to 1. So now we have this sequence of points that's in X. What does it converge to? We already said, then this thing lies in X bar. And that's by the proposition. Right, we were supposed to show that if we had 2 points that were limits of sequences of points in X, and we took a convex combination of them, that was still inside of X bar. Right? Remember, to say that, right. So you're saying that if the VKs are all in X and the WKs are all in X, that's the same thing as saying that V and W lie in X bar. So what this says is if V is in X bar and W is in X bar, then this convex combination of V and W is in X bar, and that means X bar is convex. Questions about that? Taking closures does not ruin convexity. That's the moral of that little story. So now we're getting into some actual convex geometry here. This is sort of preliminary stuff, but now we're getting into some actual convex geometry. So a hyperplane, by which I mean an affine subspace of codimension 1 inside of the vector space. Codimension means you look at the difference in dimension between the affine space and the whole space. So codimension 1 means that it's sort of one dimension less, not sort of, it's one dimension less than the ambient space. So a hyperplane, H, contained in V, I'm going to say that separates, it separates V from X if V is in the negative closed half space and X is contained in the open positive half space.
Is that supposed to be a big V or a big X? Or not?
Where did I?
Or do you say V, a big V, and then you switch to B, big X?
Where are we talking? Tell me which line.
For H contained in V.
This is a hyperplane H inside of a vector space V.
Okay.
And I want to say it separates V from a set X,
Okay.
where X is also contained in V.
Okay.
So I'm about to draw a picture which will make that a little clearer. So I'll draw the picture over here. So we have our hyperplane H here, right? And so then over here, this is going to be H bar minus, and then we want our, this is going to be our set X over here. It's going to be this thing, something like that. And what we want is that V lies over here and X lies over here on the open. So it's the open half space here, right? So the point is that this closest point here can't lie on the hyperplane. It has to, this whole set has to be contained in the open half space on this side. Is that better, Nicole? Good. Okay, so let's see. So then I want to just draw the arrow like this, just to indicate that that's the positive direction. Positive direction of what, you may ask, right? It's the positive direction of not the hyperplane. But if there's some linear function involved, then we can define the hyperplane in terms of the linear function. So what we'll say is that a linear function, function L in V star. Of course, V star is the same as V prime because this is a real vector space. So I'm just going to use star for dual. Separates that's going to be separates, and it's going to be V from X. If, and this is a little bit easier, it's going to say L of V is less than L of X for all little x in big X. Why is that the same? Think about that. Why is that the same? So if L is a function whose value on this hyperplane is constant, right? Then L of V has to be less than or equal to whatever value it takes here. So think of moving, well, anyway. V has to be, so L of V has to be less than or equal to this, whereas L of X has to be greater than this. And so that's saying that X lies in the strictly positive half space and V lies in the weakly negative half space. So it's the same definition, but in terms of a linear function instead of in terms of a geometric hyperplane. those of you comparing erasers, was also much easier for me. So the theorem is that if X is closed, the shorthand way of saying X is closed, and convex, and if you have a point V that lies outside of X, then there exists a hyperplane H separating V from X. So you can always separate points outside of convex sets from the convex sets themselves when the sets are closed. Why do I need to assume that the set is that X is closed? Maybe worth thinking about that for a second. Yeah.
Because otherwise V could be a boundary point of X.
V could be a boundary point of X. So what would happen if V was a boundary point of X? So that doesn't sound so bad, right? Let's make this like that. Make that V, make that X. Is this bad? Does that hyperplane separate V from X?
V would have to be on the hyperplane, right?
V is on the hyperplane. V is absolutely on this hyperplane. Right? Think of the L version, the linear function version, right? What is the value of this linear function at V? Well, it's whatever it is, right? What's the value of this linear function at all the points at X? It's strictly positive there, right? Strictly bigger than it is at V. So this is not a counterexample. You're still right? It could lie on the boundary, but other things have to lie on the boundary too. So if you want to make a, anyone know what a counterexample might look like? Well, so I want it to be convex. I still want X to be convex, right?
Could you see that the X contains part of the line?
Yes, so I want X to contain part of the line. So I really want it to look like this. And now I have a problem, right? If I have my point sitting over here, then if I want my hyperplane through that point, it's always going to contain points in that line segment, which is bad. So it's not to say that if X is not closed, that you can't find the separating hyperplane. It's just that if you want to guarantee that there is one, you should assume that your X is closed. So that means we need to use the closed hypothesis at some point in the proof. It has to come up somewhere because it's not true generally if we leave off the closed. Okay, so proof. So for any choice of inner product, we're just going to choose one. The norm if we take this norm to be the inner product square root like this is the usual way of doing things. This is basically saying assume that you're actually in Rn. So this doesn't involve finite dimensions. I haven't mentioned finite dimensions. So the fact that I can choose an inner product is maybe fishy. But if you want to assume finite dimension for these kinds of things, just do it for the convexity stuff. Well, this is all true in infinite dimensions, but I'm only going to give the proofs in finite dimensions.
Still have a hyperplane in infinite dimensions?
Sure. It's just take one linear function and look at its zeros, and then, right? It still makes sense to say codimension 1. And if you wanted codimension 2, you could take two independent linear functions and look at their zeros. Right? So finite codimension still makes sense in infinite dimensional vector spaces. Good question. Okay. Let's see. So this yields it leaves a function f, and it's going to be f of x, which is going to be the norm of x minus v. That's going to be a function from x to the reals And what kind of function is this? It has some properties. It is, I claim, it is continuous. That was something that we proved actually explicitly. We proved that any norm is continuous in the usual topology, the usual metric, right? It's continuous. It's bounded below. Why is it bounded below? What's it bounded below by?
0.
Yeah, 0, right? It's the norm of something, so it's automatically at least 0. And what's called proper. So proper means that, I need this picture. I have to redraw it, I'll just redraw it. Proper means that the inverse images of closed, so the inverse images of bounded sets are bounded. So proper means that F inverse of any bounded set is bounded. Why is that true? It's true by topological equivalence. So think about that for a second. What is a bounded set? Nicole, your question comes up right now. A bounded set is a set contained in a ball of some fixed radius, right? So what is a ball of some fixed radius inside of the image of this map? It's just going to be a ball around, let's say, 0 of some fixed radius. You want to know that the set is bounded, it's enough to know that it's contained in an interval from 0 to r, for some r. Because this is non-negative, so I can always start at 0. If I want it to be bounded, I can go from 0 up to whatever I want, as long as the image is contained in there, it's fine. So the point is that F inverse of the interval from 0 to r, what is that? By definition, that is the ball of radius r. It's the ball around radius r in this norm of the point V. Just look at what F is, right? F is basically distance to V. That's what you should think of it as. This norm, distance to V. So the inverse image of this bounded interval is this thing, which we know is bounded by topological equivalence. That's the point. So since X is closed, we know that F attains a minimum on X. Think about it this way. If we want to know whether F attains a minimum, let's just take any value that F does actually attain, and let's look at the set of points where F is less than or equal to that. That is bounded because it's proper, and it's closed because it's the inverse image of a closed set. So that means it's compact, so it attains a minimum. That's the point. So this is what properness gets you. It gets you that sort of well, I mean, it tells you that the inverse image of every bounded set is bounded, but that means that you can conclude that sets are compact when ordinarily all you get is that they're closed. So a continuous function on a compact set gives you a minimum, or if you like, a continuous proper function on a closed set achieves a minimum. That's what we've just shown, really. Let's say at y in X. So in the picture that we have over here, I have my linear, let's see now, let's see now, what's my function? My function is distance from V, right? So distance from V is going to have a minimum value. So distance from V, the minimum value is right over here, right? So that's my point Y. And now what I'm going to do is I'm going to set L to be the linear function that is just y minus v applied to whatever. Right, so it's going to be the linear function that's going to say, all right, well, let's take this vector here, right? And then that's going to be our L there. It's really, it's taking inner product with this thing. But inner product with this vector is our linear function. So it takes a minimum on x at y. Right? Because the inner product with this function is inner product with y, so I say v minus y or y minus v. I have to make sure I get that right. I said y minus v. Oh, good, it is y minus v. Good. So the inner product with this function, with this vector, takes a minimum at y. Or at least that's what we have to show. We're going to show that this L takes a minimum at y. Okay. How do we do that? Note that L is not zero. Why is L not zero? Yeah, well, no, it's just not the zero function.
Oh,
I mean, L is not the zero function. Why is L not the zero function then?
because y is not equal to v.
Because y is not equal to v. Why is y not equal to v?
It's not equal to x.
Yeah, since v is not in x. V is not in x, but y is in x. Therefore, y is not v. Simple enough. Good? So what I'm going to do now is I'm going to do the following. So if you give me a point over here, and let's make it just some arbitrary point here, x. And I'm going to start looking at this. Stop breaking the chalk. That's what I'm going to do. Keep doing this. So I'm going to look at this line segment that goes from y to x. And what I want to do is I want to conclude that, in fact, that the value at x is bigger than the value at y. And I'm going to use that line segment to do it. So if you give me alpha in the open interval from 0, open at the left interval from 0 to 1, and x in capital X, well, I'm going to take some norms of stuff. I'm going to take norms of points along this line segment. Okay, that's what I'm going to do. So alpha is going to take me from y to x, and I'm going to take norms of points along that line segment. So I'm going to take, so what's the norm? I have y minus b squared, square norms, fine. That's less than or equal to, I claim, this is going to be now y plus alpha times x minus y, right? That's going to give me some point along that arc where the alpha tells me how far to go. Yeah? And now I'm going to take minus b squared. Why is this true?
Because alpha is greater than 0, so you're getting the norm of something that's greater, or not the norm squared.
Well, but how do I know that? How did I choose this, this norm and so on, right? This is my function f in some sense, right? And the point is that this function is minimized at y on x. This is some arbitrary point in x in some sense. So this is an arbitrary point in x. This is the point y in x. And we know that this function takes its minimum at y. That means whatever the value is at this point, it has to be at least the value at this point y. And so this thing is just because it's a min. So y is a min. Yeah, that's the reason why. So parse this as, this is a point in x. This is a point in x, but this is the point at which the function that we're applying takes its minimum value. I mean, we actually said that the function without the square takes its minimum value, but squaring it doesn't change anything because it's positive. Okay, now I can rewrite this as y minus v, so put the minus v over there, and then plus alpha times x minus y. That's just a rewriting, no biggie there. But now I can expand, because this norm comes from an inner product, I can now expand this thing. Let's expand it, shall we? So I'm going to think of it as this piece and this piece. So what's the norm of this thing squared? Read it off to me. It's just the binomial theorem, right? It's going to be this squared plus 2 times this, right? So this is going to be y minus v squared plus 2 alpha, and now it's going to be inner product of, let's see now, y minus v and x minus y, right? That's the inner product of this and this, but I can pull the alpha out because everything's real. Plus, and now alpha squared, norm of x minus y squared. Agreed? Okay, so now what do? Now I cross stuff out. On the left-hand side is a y minus v squared. On the right-hand side is a y minus v squared. Okay? Now on the left-hand side is 0. So I'm now going to cross out the alpha and cross out the square there. Because I can divide by alpha, it's a positive number. Right? Remember, alpha was in the interval from 0 to 1, not containing 0. Okay. Now what? So this thing, that's going to be minus 2 alpha, oh, forget the alpha, and it's going to be v minus y and x minus y. I don't know why I wanted the minus 2 there. I don't care about that. This is the law of cosines, but let me not go into that. I just don't need that. So what this implies, so now I have my 0, I have my less than or equal to, and now I have my whatever's written over here, which is going to be 2 L of x minus y, right? This thing is L of x minus y, just by definition of L. And it's going to be plus alpha times the norm of x minus y squared, right? So now what I'm going to do is I'm going to let alpha go to 0, and this implies that now L of y is less than or equal to L of x. Right? When alpha goes to 0, this term disappears. The 2 is now irrelevant, and you get L of x minus L of y. So you get 0 is less than or equal to L of x minus L of y, which means that L of y is less than or equal to L of x. Okay, so what we just showed by a fairly long-winded argument is that this linear function was reconstructed specifically so that L of y would, so that it would be minimized at y. We just showed that it is in fact minimized at y. Great. What can we say about L of v? L of v is less than L of y. We already knew that, right? That's because v was not in x, but y is in x. That's because L of y minus v is equal to the norm of y minus v. Just the norm of y minus v, so squared. And that's strictly positive. That's because it's the same reason that the function L is not 0. So we get that L of v is less than L of x for all x in x. So how did that proof basically go? The proof basically said the following. Look, we take v outside of x, and we show that the distance to v, whatever distance we're gonna just choose a distance basically. We're gonna say the distance from v to x is non-zero, and we can choose there's a point where it takes a minimum. And then what we say is, well, because x is convex, we can draw a straight line from that minimum to anywhere else in capital X. And by going along that straight line from y to our little point little x, we know that the sort of the distance increases, or the value of this linear function increases. That's what we just did. So we use convexity. We use closedness to say that y is a minimum. We use convexity to draw the line segment from y to x. Okay. So applications of this occur all over the place. They occur in optimization. They occur in support vector machines. Anyone here know what a support vector machine is? Yeah, it's basically this. What you want to do is you want to say that there's some data points over here and some data points over here, and you want a hyperplane that separates the two as best as possible. Yeah, this kind of stuff is relevant to that. Okay. So now that was separating hyperplanes. Now let's do support hyperplanes, which is going to feel very similar. H is a support hyperplane of X at a point little v in capital V. So it's not necessary to think that little v is in X. If you want V lies in H and X is contained either in the closed half space, closed positive half space, or the closed negative half space. So the picture in this case is, I guess I'm going to erase that L y minus v right here, and then draw my picture over here so that it's in the sort of the big camera. So this is going to be my okay, this is going to be my X, like this, and my hyperplane will be this thing over here. So this is going to be H, and that's going to be a linear function that does it. That's the closed positive half space. And I want V to be in there. There's my point V. There we go. So what's the difference between being a support hyperplane and being a separating hyperplane? You have to look back at the definitions. One thing, I want V to be in H in this case, as opposed to the separating hyperplane, whereas I want V to be on, this closed half space. But for a separating hyperplane, if V was in this closed half space, I could always move the hyperplane up so that it was actually containing V. So in that sense, there isn't really much of a difference between separating and support. The point about support is that X is required to be in the closed half space instead of X being in the open half space. So in some sense, this X can be closer to the hyperplane. So the supporting hyperplane can be closer to X because it can actually, even if X is closed, this hyperplane can go through a point of X.
So are all support hyperplanes separating hyperplanes, but not vice versa?
I think it's the other way around. I think every separating hyperplane is a support hyperplane. Except that I want to be able to say that for a separating hyperplane, I want to be able to say that V doesn't lie in the hyperplane. I want to be able to choose my hyperplane so that it sits between X and V. V could lie on the separating hyperplane, but it doesn't have to. For a support hyperplane at V, I want V to lie in the hyperplane itself. But yes, I mean, your question is basically, the answer is yes. You can always arrange that if you're given a separating hyperplane, you can just translate it so that now it goes through V, and now it's a support hyperplane through V.
But isn't this a counterexample?
To what?
Like, this is a support plane, but
I said every separating hyperplane is a support hyperplane as long as it goes through V. This does not separate V from X.
yeah.
So there's no, I didn't say every support hyperplane is a separating one. I said every separating one gives you a support one. If this was separating and contained V, then it would be a support hyperplane. It's not separating, so there's nothing to conclude.
But still, again, if V was, if V was not in X, but still we had a few points of X, okay.
Yeah, if V was not in X and this was a separating hyperplane, then it would be a support hyperplane. Yeah, it's easier to be a support hyperplane in that sense. Okay, the condition is weaker in that X only has to be inside of the closed half space instead of X being inside of the open half space. So you don't have to sort of move X over a little bit if it was closed, right? So if X is closed and it intersects this hyperplane, that's fine for support. It's not good for separating.
So can there be any other points on H that are in X?
Sure.
So, okay, if we exclude V from X and we include another point of H to X.
This is also a support hyperplane at V. It's not separating, but it is support. Fair enough?
Mm-hmm.
Good.
Does V have to be in X, or can X be open?
Nope, it doesn't have to be in X. V can be completely far away from X. And it could also be on the boundary of X. Without actually being in X, that would also be fine. Yeah. Okay, so here's the theorem. That the X is convex and V lies in the boundary of X. And it doesn't matter, as Noah just asked, it doesn't matter whether it's in X or not in X. It just matters whether it's in the boundary of X. Then there exists a supporting, or a support, if you like, a support hyperplane, called supporting hyperplane of capital X at little d. So the intuition for this is well, I'd say it's intuitive enough. That it's the following. It's that you can always sort of find hyperplanes that sort of, if you pick X and if you pick a point of the boundary, then you should sort of pick hyperplanes that sort of get closer and closer and closer until you actually hit at the desired point. So if you didn't know about this blue line first, you'd sort of take a linear function that's close and you sort of keep moving it and moving it and moving it, and you take a limit until you hit that point. It's kind of how you try to do things there. Then as you find, just take a line going out here, take a separating hyperplane for this, separating for this, separating for this, separating for this, separating for this, limit, 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 until you, again, the limit is going to be a support thing. That's the idea. So proof, X is contained in the closed, let's say, positive half space, implies that the closure is contained in the closed positive half space, in the closed positive half space. So I may as well assume that X is closed. Just replace X with its closure. So just assume that X is equal to its closure. So for K, which is a non-negative integer, pick, let's say Vk outside of X, and Lk, that's going to be in this sphere of dimension n minus 1. So this is going to be, so this is assumed finite dimension. Assume that the dimension of V is finite. Again, I'm always, in the proofs here, I'm just going to assume finite dimension. Although this is true without finite dimension. So let's pick, so we have our linear function Sn minus 1. What is Sn minus 1? Where Sn minus 1 That's going to be the set of linear functions, W, I think I called it, W in V star, such that their length is 1. That's a subset of V star. And I want to pick this linear function to be separating Vk from X. Now, if you're worried about what do I mean by length, you can choose a norm if you want, or you can assume that this is Rn. I don't care in what generality you want to understand this, but you can always choose a norm if you like.
Did you write K in the natural numbers?
Yes. K is in the natural numbers. Just choosing a sequence, I did exactly what I said I was going to do. I'm just going to take a sequence of points approaching V, and then I'm going to take separating functions and then show that the limit is a support one. That's all I'm going to do. So assume that Vk approaches V, let's say as k goes to infinity. Okay, so Sn minus 1 is compact, that is closed and bounded. So this sequence Lk has a convergent subsequence. Again, not something I'm going to prove in this class, but hopefully this is giving you some idea that compact sets are nice and useful. So that means, what that means is if I select, so if I just choose a set of points converging to V and then look at the hyperplanes, if I was converging to something that looked in this picture like this, then I could have been choosing hyperplanes that look like this and hyperplanes that look like, let's see now, this, right? And they could bounce this red one, blue one, red one, blue one, red one, blue one. Those wouldn't converge, but then there's always going to be a convergent subsequence. So I can just restrict to just the blue ones or something like that. So let's replace Lk with that convergent subsequence to get that the Lk's converge to L. By the way, if you were skeptical about considering the dual space as a different space from V itself, this should convince you that you should think of the dual space as being its own vector space. This convergence is occurring in V star. It's not occurring anywhere inside of V. So we want to think of V star as being its own vector space in order to make this argument. Okay, so for all x in X, what we have is that the sequence Lk of X minus Lk of Vk, what do we know about that for K in N? We know that that converges to L of X minus L of V. What can you tell me about what's inside here? Non-negative, because it's separating. And this implies that this thing here is also non-negative, because the limit of non-negative numbers is still non-negative. You can't jump past 0 by taking a limit like that. And this implies that we take H to be just Y V such that L of V equals L of Y, then this suffices. So we did exactly what I said we were going to do. We're just going to take a set of points approaching V. We're going to take separating hyperplanes, show that in that collection of separating hyperplanes, there is a convergent sequence of separating hyperplanes, and that convergent sequence converges to a support hyperplane. That's all we've done. Last concept for the day. Last concept that we're going to do in convexity, actually. So for x convex, a point of x is an extreme point if V does not lie in the convex hull of x take away V. That is, in all the points of x, you need to have V. If you want to take the convex hull of a subset of x and get x back, you need to have V in there. Lemma. This occurs if and only if V does not lie in any line segment between x and y, whenever V is not equal to x in capital X, and V does not equal y, which is in capital X. So as long as V is not either x or y, it can't be in the line segment containing x, between x and y. What that says is that 2 points suffice to witness the non-extremeness of V, right? I want to check that a point is not extreme, show that it lies in the convex hull of just 2 points. How do you prove that, by the way? It's easy enough. If you have that V was in the convex hull of sort of, a bigger subset, then write it as a convex combination and then split the convex combination into 2 pieces. And then one piece will be x and the other piece will be y. Okay, so here's just some pictures. So if I have something like this, and then I something like that, and something like this, something like that. There we go. So where are the extreme points in this thing? So this is. Yeah, so where are the extreme points? I'm going to mark them in red. Is this point over here extreme? No, because it's in the convex hull of this one and that one. Okay, so generally speaking, what do the extreme points look like? How would you describe them in words? In this picture. The curved parts. Here's a question. Is this point extreme? Yeah, it is, because in order to get this point, you have to take a point that's further along this line segment than this point, but as soon as you go past this point, you're no longer in X. In order to get this one as a convex combination of stuff that's in X, you have to use this point itself. So that point is indeed extreme, so all these points are actually extreme. Okay, so the theorem is that if x, or one of the theorems, if it's bounded and convex, then each supporting hyperplane contains an extreme point. It contains an extreme point of x. You want to find an extreme point, suffice it to look inside of a support hyperplane. That's what this says. So proof, again, assuming that the dimension is finite. So let's fix a support hyperplane. We need to show that there's an extreme point of x in there, right? That's the claim? Yeah.
I thought that x could be away from support hyperplane. Like, I thought that the definition was that x could be different from that hyperplane.
Oh boy, by the definition I gave, that's true.
You say like if
Yeah.
whatever plane that contains point in X, then there's an extreme.
Yes, let's say that. Let's leave it like that. I need to decide whether or not I want to make support hyperplanes intersect the closure of X or not. So let's see if H not empty. Yeah, I need to decide whether I want to do that. Okay, so we need to show that if the intersection is non-empty, then it contains an extreme point. So the claim that I want is that if V and Y is extreme, oh, what's Y? Let's set Y the H intersect X, which is now non-empty. So let's say that if you have a point, well, this would still be true. Even if the intersection was empty, this claim will still be true. Because what it's going to say is an extreme point in Y is extreme in X, but if there are no points in Y, it's vacuously true. But that being said, the theorem wouldn't be true if I didn't assume this. That's the real problem. So I claim that every extreme point in Y is extreme in X. So this implies the theorem by induction on the dimension of the ambient space. Because now, so Y sits inside of a hyperplane, and the hyperplane has dimension 1 less than the dimension of V. And so if Y has an extreme point inside of H, and so does S, and then X has an extreme point inside of H. Yeah. I may change just the definition of support hyperplane to force it to intersect the closure. That might be what I do in the future. I'll have to pick. So the proof of the claim. So let's pick L orthogonal to H. Have I used an inner product for this? I'll end in a second. And I want L of X to be greater than or equal to L of V. This is a linear function. This is a hyperplane, and all I'm saying is that L should be constant on H. This is not using an inner product. It's using the pairing between linear functions and points at V. And for something to be orthogonal to, for a linear function to be orthogonal to a hyperplane just means that that linear function is constant on a hyperplane. It says that H is contained in a level set of L. In fact, it is a level set of L. Okay, so V, if that's alpha X plus beta Y with XY in capital X and alpha plus beta equals 1, that implies that L. So I'm saying that suppose that V is a convex combination of 2 points of X. That's what this says. Then I claim that L of V, what's that? That's alpha L of X plus beta L of Y. But remember, see, L of X and L of Y are supposed to be bigger than or equal to L of V. So I'm adding up two numbers that are greater than or equal to L of V with coefficients that sum to 1. What can you tell me about L of X and L of Y? Remember, this thing is greater than or equal to L of V. That's greater than or equal to L of V. Alpha plus beta was 1, so then this sum is at least L of V. Yes? And it's equal to L of V if and only if this one's L of V and that one's also L of V. So L of X, says that L of X is equal to L of V is equal to L of Y. Just think about what happened if this one was L of V plus epsilon. Then you'd get alpha times epsilon plus alpha L of V. Beta plus, so beta times something, and what you get is the alpha times L of V plus beta times L of V plus something else, and the something else has to be 0 because this is an equality. That means that these things have to be equal. And so that implies that X is in H and Y is in H. That's it, because to be in H just means that L of U equals, so L of the whatever it is has to equal L of V. That's what it means to be in H. So that's a rather simple proof. How to use linear functions. Definition, a subset S inside of V has convex hull. And we've sort of already defined this. And it's going to be conv S, which is going to be the convex combinations of points in S, which is, I claim, the smallest convex set containing S. That's a proposition. But it follows directly from the fact that a convex combination of convex combinations is a convex combination. And so this is property 8. Property 8 said this thing when S was a finite set. But the point is that but the point is that a convex combination of points in S only uses a finite set of points in S at a time. So you're only ever using a finite set of points in S when you're making a convex combination. So S needn't have been finite to begin with in order for that to hold. Okay, this is the last thing we want to say about convex sets. This is called the prime-Millman theorem. It holds an infinite dimension, but we're only going to prove it for finite dimension. And it says that if X is bounded and convex, in infinite dimension, you probably want to say compact, then, so it's closed, bounded, and convex, then I claim that X, or they claim that X is the convex hull of the extreme points of X. So in this example, right, this thing is equal to the convex hull of this, this, and this. And that's what this thing says. Well, polytope is always going to be a convex hull of its vertices. And you have some exercises about this, what happens when the thing is not bounded. What kinds of things can you say? Proof. So let's suppose that X contains some subset Y, which I guess I'll draw in. Okay. Red here. So Y is going to be that red thing there. Let's suppose X contains that subset Y with Y closed and convex. So what you should think is that y is going to be the convex hull of the extreme points, and you want to suppose that it's not actually equal to x. What you're really going to show is that if if x is contained in, if x is not contained in y. Remember, so x contains y. So the point is, what if x is not equal to y? What you want to show is that if x is not equal to y, then there is an extreme point of x that doesn't lie in y. In this picture, there is an extreme point of x that does not lie in y. That's going to be the idea. So as long as y is a proper subset, then it misses an extreme point, which means that the convex hull of the extreme points has to be all of x. So this means that there's going to exist a point v in x take away y with L separating v from y, right? So in this picture, I guess what I'm looking at is there's now a separating hyperplane here, right? So x is compact, which means closed and bounded. Then L contains a minimum at some point x in capital X. So that's the point here. I'm going to rename x, whereas it was b, right? So this linear function is going to attain a minimum at some point of x, and that's going to be the point that I want. So note that L of x is less than L of all of capital Y, and that's by separation. Right, that's the definition of separating hyperplane. So if we take H to be the set of points in V such that L of W equals L of X, then this supports capital X at little x by construction. Right? The whole point was that it's a minimum. This is a minimum. So if this is a minimum, then this is a support hyperplane for x, capital X. So the previous theorem, this theorem over here, says that there's always an extreme point in a support hyperplane, as long as the intersection is not empty, which it is because it contains this point x. Yeah? So the previous theorem, which I'm now erasing, previous theorem means there's an extreme point of capital X in little in H, and this implies that capital Y can't contain all extreme points of capital X. Thus, we have that X is contained in the convex hull of the extreme points of X, and the other containment is really dumb. Now, so again, the summary of that proof is, suppose you have a convex subset that's strictly contained inside of X. If it's a closed convex subset strictly contained inside of X, then it misses an extreme point. What you're really saying is that it misses a support hyperplane, which therefore contains an extreme point. That's really how the proof said. Any proper convex subset of X misses a support hyperplane, which therefore contains an extreme point that wasn't in the subset. That's all it's really trying to say. Okay. So next time we're going to start with subspaces and Grassmannians, these kinds of things. So it's a very different topic. So I would review, do the reading before next lecture to help get yourself familiar with, refamiliarize yourself with row reduction and invertible matrices and multiplying by invertible matrices and taking the combinations of rows and columns by multiplying by matrices on the left and right and these kinds of things.